What if I told you that 98% of the high-energy X-rays flooding our universe come from completely unknown sources? For over 60 years, astronomers have stared into the depths of space, armed with the most advanced telescopes ever built, only to be met with a cosmic whisper that defies all explanation. It's not a star, not a galaxy, not a black hole. It's something far more mysterious, something that permeates every corner of the cosmos. This haunting glow is known as the cosmic X-ray background, and it remains one of the greatest unsolved puzzles in the history of astronomy. Imagine turning on a radio and hearing a faint, static hum coming from every station at once. No matter how you tune the dial, the sound is always there, a ghostly presence that hints at something profound happening just beyond your reach. That's what scientists experience when they look at the sky in X-ray light. This all-pervasive glow is not just background noise, it's a signal, a cosmic message written in a language we are still struggling to decode. It whispers of colossal energies, unimaginable distances, and phenomena that challenge everything we think we know about the universe. In this video, we're going to journey together into the heart of this magnificent mystery. We'll explore 25 of the most profound enigmas hidden within the cosmic X-ray background, from its unexpected discovery in the 1960s to the cutting-edge missions still trying to unravel its secrets today. This isn't just a story about science, it's a story about human curiosity, perseverance, and our endless drive to understand the cosmos. You're about to witness one of astronomy's greatest detective stories, a puzzle that has captivated generations and continues to inspire wonder and awe in everyone who dares to look up and ask, what is really out there? Our journey into the unknown begins not with a complex space telescope, but with a humble, unassuming rocket named Aerobee 350. It was 1962, and a brilliant Italian physicist named Riccardo Giacconi had a seemingly straightforward plan. He and his team wanted to answer a simple question: does the moon, our closest celestial neighbor, give off X-rays? The prevailing wisdom at the time suggested the sky in high-energy light should be almost completely dark, a silent void. To test this, they mounted a crude but revolutionary X-ray detector on the nose cone of that rocket and launched it high above the Earth's atmosphere, which blocks these energetic rays from reaching the ground. What they found upended all of astronomy. Instead of a dark sky or a single X-ray source from the moon, their instruments detected something astonishing and completely unexpected. A faint, uniform glow of X-rays was coming from everywhere at once. It was like stepping into a dark room expecting nothingness, only to find yourself bathed in a soft, ethereal light with no obvious source. The data was so puzzling that some of Giacconi's own colleagues initially thought it must be a mistake, an artifact of the detector itself or some kind of interference. But the signal was real. They had accidentally stumbled upon the first evidence of the cosmic X-ray background. This discovery sent shockwaves through the scientific community. It was a classic case of a serendipitous finding that completely rewrites the rules. Imagine setting out to find a single candle in a vast, dark field, and instead discovering the entire field is mysteriously illuminated from some unseen source. For decades, this pervasive glow remained an enigma, a cosmic secret that taunted astronomers. It was the ultimate background noise, and deciphering its origin became one of the highest priorities in astrophysics. The significance of this accidental discovery was so profound that 40 years later, in 2002, Riccardo Giacconi was awarded the Nobel Prize in Physics. The committee recognized that his team's seemingly failed experiment to find lunar X-rays had, in fact, opened an entirely new window on the universe, revealing a cosmos crackling with high-energy activity we never knew existed. Yet this incredible discovery presented an even deeper puzzle, one that has haunted astronomers for decades. If this glow comes from countless individual sources, why does it appear so perfectly uniform in every direction we look? This is the baffling paradox of the cosmic X-ray background's uniformity. Think of it like standing in the middle of a vast, dark forest at night, surrounded by millions of fireflies. You would expect to see clusters of light where the fireflies swarm together and dark patches where there are none. But instead, you see an impossibly even, unchanging glow in every single direction, as if the entire forest were coated in a single luminous sheet. That defies all logic and expectation. In our universe, matter isn't spread out evenly like butter on toast. It's lumpy. It clumps together under gravity to form stars, which gather into galaxies, which themselves collect into massive clusters and long filaments, creating a great cosmic web. We see this clustering in visible light, and we absolutely see it in the individual X-ray sources we can identify, like brilliant quasars or the hot gas surrounding galaxy clusters. They are decidedly not uniform, so the fact that the unresolved background is so perfectly smooth or isotropic is a profound contradiction. It forces us to ask a terrifying question: are we missing something fundamental about how the universe works? Statistically, creating such a smooth glow is incredibly difficult. For the light to average out to such uniformity, the sources responsible would need to be impossibly numerous and distributed across truly vast cosmic distances. It would require that the entire observable universe, from its earliest epochs to the present day, is filled with an uncountable number of these objects, all shining with a similar intensity. It's a proposition that pushes the limits of what our models can explain. Some theorists have proposed that this uniformity might be an illusion, a trick of perspective caused by the immense, mind-bending scale of the universe, but the math is extraordinarily challenging. This paradox has sparked intense debate and led to some of the most fascinating theories in modern cosmology. One compelling idea is that we are seeing the collective glow from the very first supermassive black holes in the universe, ones that formed so early and in such abundance that their light has been stretched and diluted across all of space-time. Another, more radical suggestion is that the glow isn't from discrete sources at all, but rather evidence of something more exotic and fundamental, perhaps a process involving dark matter or even a previously unknown property of space itself. The uniform glow doesn't just hint at unknown objects, it whispers that our very understanding of the cosmos on the largest scales might be incomplete. But the mystery of the uniform glow is just one layer of this cosmic puzzle. To understand the true depth of what we're dealing with, we need to confront an even more fundamental problem, one that strikes at the very heart of what the universe is made of. This is the astonishing case of the missing matter. When cosmologists calculated the total amount of ordinary matter, the stuff that makes up you, me, the planets, and all the stars that should have been created in the Big Bang, they arrived at a very specific number. This ordinary matter is known as baryonic matter, named for the protons and neutrons that form the building blocks of atoms. Yet, when astronomers added up all the matter, they could actually see with telescopes all the stars, galaxies, and glowing gas clouds. They came up horrifyingly short. They could only account for roughly half of what the models said must be out there. For decades, this was a huge embarrassment in astronomy. It was as if you carefully counted all the ingredients for a cake, but after baking it, half the flour and sugar had simply vanished from the finished product. Where did it go? This became known as the missing baryon problem, and it seemed to suggest a catastrophic flaw in our understanding of the universe's recipe. This is where the cosmic X-ray background transforms from a mere mystery into a vital clue. Scientists theorized that this missing ordinary matter hadn't actually disappeared. Instead, it might be hiding in plain sight, but in a form we simply couldn't detect with traditional telescopes. They proposed that this matter exists as a vast, diffuse web of incredibly hot gas, strung between galaxies and clusters in the cosmic web. This material is known as the warm-hot intergalactic medium, or WIM for short, and it's not just warm, it's searingly hot with temperatures ranging from hundreds of thousands to millions of degrees. At these tremendous temperatures, the gas doesn't behave like the cold gas we're familiar with. It becomes a state of matter called a plasma, where atoms are ripped apart into a soup of free-flying electrons and atomic nuclei. A gas this hot doesn't give off visible light. It doesn't glow in a way our eyes or optical telescopes can see. What it does do, however, is radiate profusely in X-rays. This faint, pervasive emission from this superheated, invisible web is a prime candidate for what makes up a significant portion of the cosmic X-ray background. The very glow that confused astronomers for so long might be the long-sought signature of the universe's missing material. Proving this theory, however, is a monumental challenge. Detecting the WIM is like trying to see the faint, shimmering heat haze rising from a road on a distant horizon. Its signal is incredibly weak and blended with the light from other, brighter X-ray sources. To find it, astronomers have to become cosmic detectives looking for specific telltale signs. One method is to search for the subtle absorption lines imprinted on the light of distant, brilliant quasars. As that light passes through filaments of the WIM on its billions of years' journey to us, the superheated gas absorbs very specific wavelengths of X-ray light, leaving a unique fingerprint that we can, with incredibly sensitive instruments, detect. Another approach is to use the CXB itself. By carefully subtracting the light from all the known point sources, the quasars and galaxies we've already identified, the remaining, truly diffuse glow could be the collective murmur of this warm, hot intergalactic medium. It's the sound of the universe's hidden skeleton finally revealing itself. Solving the missing baryon problem would be a monumental achievement, confirming that our fundamental models of the cosmos are correct and that we finally know where to find all the ordinary matter. The cosmic X-ray background, therefore, isn't just a mystery to be solved. It's a map leading us to the hidden half of everything. So if the missing matter is one piece of this puzzle, another major suspect emerged early on, one so brilliant and powerful it seemed like the perfect culprit. This brings us to the supermassive black hole connection. At the heart of nearly every large galaxy, including our own Milky Way, lies a gravitational monster, a supermassive black hole weighing millions or even billions of times more than our Sun. While these black holes themselves are invisible, when they actively feed on surrounding gas and dust, the material doesn't just vanish. It spirals inward, forming a superheated accretion disk that glows with unimaginable intensity, outshining entire galaxies. This phenomenal engine is known as an active galactic nucleus, or AN. The light from these feeding frenzies is so energetic that a significant portion of it is emitted as X-rays. For a long time, astronomers believed they had found the definitive answer to the cosmic X-ray background. The thinking was beautifully simple. If you take all the AGN across the entire universe, across all of cosmic time, and add up their collective X-ray light, it should perfectly explain that uniform, all-pervasive glow. It was an elegant solution, tying one of the universe's most energetic phenomena to its greatest background mystery. Telescopes like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton were launched with this very goal in mind, to resolve the faint background glow into a sea of individual, point-like AGN. And they succeeded to a point. These incredible observatories did find thousands upon thousands of previously hidden AGN, their brilliant X-ray beacons piercing the cosmic dark. But instead of solving the mystery, this deep look only deepened it. When scientists meticulously added up the light from every single AGN they could find, they came up short. The combined X-ray flux from all these monstrous black holes could only account for a portion of the total background, perhaps less than 80%. A significant fraction of the glow remained stubbornly unresolved. It was like meticulously counting every bonfire in a vast valley at night. only to realize their combined light still wasn't enough to explain the eerie, ambient illumination bathing the entire landscape. A major source was still missing. The problem wasn't just a matter of quantity, it was also a question of quality of the type of light. The unresolved portion of the background seemed to be softer or less energetic than the hard X-rays typically blasted out by the most powerful AGN. This suggested that whatever was producing the remainder wasn't just more of the same. It had to be something different, something either more numerous, more distant, or fundamentally unlike the active galactic nuclei we already knew about. One compelling theory is that we are missing a huge population of obscured AGN black holes that are shrouded in thick, dense cocoons of gas and dust. This material would absorb their highest energy X-rays, allowing only the softer, lower energy radiation to escape and contribute to the background glow. Finding these hidden monsters is a tremendous technical challenge. It requires looking in different wavelengths of light like infrared, which can pierce the dusty veils. But even accounting for a hidden population, the numbers still might not perfectly align. This gap forces us to consider other, even more exotic contributors. Could it be the collective sigh of the very first generation of stars, massive behemoths that lived fast, died young, and flooded the early universe with radiation? Or perhaps it's the signature of countless stellar mass black holes and neutron stars, the remnants of dead stars scattered throughout the halos of galaxies. Each possibility opens a new door to a deeper understanding of cosmic evolution. The AGN connection, therefore, is a story of a promising lead that turned out to be a crucial piece of the puzzle, but not the entire solution. It showed us that while supermassive black holes are titans that shape their galaxies and contribute enormously to the high-energy universe, they do not act alone. Their powerful voices form a dominant part of the cosmic chorus, but they are blended with the fainter whispers of other, still unidentified singers. This realization shifts the investigation, pushing us to look for fainter, more numerous, or more obscure sources that have, until now, remained hidden in the shadows of these brilliant giants. So if supermassive black holes are a major piece of the puzzle but not the complete picture, where is the rest of the light coming from? This brings us to a secret army of cosmic engines, ones that are deliberately hiding in plain sight. We now turn to the hidden population of obscured active galactic nuclei. Picture the most powerful energy source in the universe, a supermassive black hole feasting on matter. But then imagine it shrouded within a massive, thick cocoon of gas and dust. This isn't a thin veil, it's an incredibly dense cosmic fog bank that swallows light. These are known as obscured AGN, and they are the universe's best-kept secret. The key to understanding their hiding place lies in a specific, almost mythical classification: Compton-thick objects. The name comes from the Compton effect, a principle in physics where high-energy X-ray photons scatter off electrons. For an AGN to earn this title, the cloud around it must be so impossibly dense that it has a column density of at least 10 to the 24 atoms per square centimeter. To put that astronomical number into perspective, you would need to pack all the air from Earth's entire atmosphere into a tube just 1 square centimeter across. That's the level of obscurity we're talking about. This thick shroud acts like a brilliant cosmic disguise. It effectively blinds our optical telescopes as visible light cannot hope to penetrate it. Even many X-ray telescopes struggle because while they can detect some lower energy X-rays, this dense material absorbs or scatters the highest energy ones, the very signature that makes an AGN easiest to identify. This creates a huge problem for astronomers. It's like trying to take a census of a city during an incredibly dense perpetual fog. You can hear the muffled sounds of activity and see the faint, diffused glow of lights, but you cannot see the buildings themselves, count them, or understand what exactly is powering each one. We know these Compton-thick AGN must be out there because our models of how galaxies and black holes evolve demand it. In fact, some theories suggest that this hidden phase might be a common, even necessary, stage in the life of a supermassive black hole. But because they are so difficult to spot, we have no clear idea of how many there truly are. They represent a massive gap in our inventory of cosmic energy producers. This is why these hidden monsters are such a compelling suspect for the remaining portion of the cosmic X-ray background. While the unobscured, blazing bright Aegean contribute their powerful, high-energy X-rays, the obscured population would be leaking out only their softer, lower-energy radiation. Their combined, muffled whisper from across the cosmos could perfectly account for that softer, residual glow that the brighter Aegean couldn't explain. It's the sound of a cosmic choir singing from behind a curtain, their powerful voices softened and blended into a uniform hum. Detecting them, however, is a technological nightmare that requires a multi-wavelength strategy. Since their visible light is blocked, we cannot use optical telescopes. Since their highest energy X-rays are absorbed, standard X-ray observations often miss them. Astronomers have to become clever detectives looking for indirect clues. One method is to search in the infrared part of the spectrum. That thick shroud of dust and gas doesn't just absorb light, it heats up. And when it heats up, it re-radiates that energy as a strong, telltale infrared glow. So, a source that is faint in X-rays and invisible in optical light but incredibly bright in infrared is a prime candidate for a hidden Aegean. Another technique involves looking for specific, subtle features in the X-ray spectrum we can detect. The dense material surrounding the black hole doesn't just absorb light, it also reflects it. This can create a unique fluorescent signature, most notably a sharp peak at a very specific energy level corresponding to iron atoms. Spotting this faint iron line is like seeing the glint of light off a hidden object. It confirms the presence of the massive structure obscuring the central engine. New generations of X-ray telescopes with vastly improved sensitivity and spectral resolution are being designed specifically to hunt for these faint fingerprints, hoping to finally pull back the curtain on this hidden population and complete our census of the universe's most powerful engines. But while supermassive black holes and their hidden cousins are prime suspects, they are not the only powerful sources flooding the universe with high-energy light. We must now turn our attention to the largest gravitationally bound structures in the cosmos, colossal galaxy clusters. These are not mere collections of stars, they are immense cities of galaxies, containing thousands of members all swarming around a common center of gravity, held together by the immense pull of their own dark matter halos. And within these vast metropolises lies a secret ingredient, a colossal atmosphere of superheated gas. The space between the galaxies in a cluster is not empty. It is filled with a thin, yet incredibly hot plasma that can reach temperatures of tens of millions of degrees. This gas is heated to such extreme temperatures primarily by the sheer gravitational crush of the cluster itself. As matter fell into the cluster's potent gravitational well over billions of years, it gained enormous speed and then crashed into other incoming material, converting that kinetic energy into intense heat. This process creates a massive, shimmering ball of ultra-hot gas that envelops the entire cluster, containing more mass than all the stars in all the galaxies within it combined. And this is where the physics gets fascinating. A gas this hot doesn't glow like a star, it glows through a process called thermal Bremsstrahlung radiation. The name comes from German, meaning breaking radiation. Here's how it works. In the superheated plasma, free electrons are zipping around at tremendous speeds. As one of these electrons passes near the positively charged nucleus of an atom, it is deflected from its path by the electric attraction. It effectively breaks for a moment. This sudden change in speed and direction causes the electron to lose a bit of energy, which is promptly radiated away as an X-ray photon. This process is happening countless trillions of times every second throughout the vast volume of a cluster, making the entire structure shine brilliantly in X-ray light. It acts like a colossal, diffuse light bulb hanging in the void. Given their immense size and brilliance, astronomers naturally assumed that galaxy clusters would be major contributors to the cosmic X-ray background. It seemed logical that if you added up the collective X-ray glow from every cluster in the observable universe, it would account for a significant chunk of that mysterious uniform haze. But when they finally did the math, the results were startling and deeply revealing. Instead of being a dominant player, clusters of galaxies contribute less than 10% of the total background. This was a profound surprise. The largest structures in the universe, blazing with X-rays, are mere bit players in this cosmic symphony. This discovery tells us something incredibly important about how structure formed in our universe. The fact that clusters contribute so little means that the majority of the X-ray background must be originating from processes that occurred before these giant clusters ever fully assembled. It points the finger of suspicion back to an earlier, more chaotic era of the cosmos. The bulk of the glow seems to be coming from a time when the universe was younger, when matter was distributed in a more fragmented way, and when the first generations of supermassive black holes and stars were just beginning to violently turn on. The relative faintness of clusters in the background is a powerful clue that the story of the CXB is written not in the present-day universe of grand structures, but in its formative, adolescent years. It forces our investigation to peer back across deeper stretches of cosmic time, to an epoch when the universe was a very different place. This realization that galaxy clusters are not the primary source invites us to look closer to home, or at least to a far more common and familiar class of object. We now arrive at a quieter, more numerous, and utterly surprising suspect in our cosmic investigation, the humble star. This is the stellar contribution conundrum. For a long time, astronomers considered normal stars to be bit players in the high-energy universe. Our own sun, for instance, emits a faint X-ray glow from its superheated corona, but it's a tiny whisper compared to the roaring energy of an active galactic nucleus. The logical assumption was that if you added up the X-ray light from every star in every galaxy, it would be a mere drop in the cosmic bucket, completely drowned out by the titanic power of supermassive black holes. But the universe, as it so often does, defied our expectations. As our X-ray telescopes grew more sensitive, they began to pick up a faint, diffuse haze of low-energy X-rays emanating not from the distant depths of space, but from much closer within our own Milky Way galaxy and its nearby neighbors. This emission couldn't be explained by the hot gas of galaxy clusters or the powerful jets of AGN. The hunt for its source led astronomers to a stunning conclusion. A significant portion of this soft X-ray background was coming from vast populations of perfectly normal stars. This was a paradigm shift. It meant that the collective sigh of countless stellar systems was a major contributor to the cosmic glow, particularly at the lower energy end of the spectrum. The real powerhouses, however, aren't single stars like our Sun. The true X-ray champions of the stellar world are binary systems where two stars are locked in a tight gravitational dance. In these intense relationships, one star has often reached the end of its life, leaving behind a super-dense corpse, a white dwarf, a neutron star, or even a stellar mass black hole. If its companion star is still a vibrant, hydrogen-rich giant, a spectacularly violent transfer of matter can begin. The immense gravity of the dense corpse relentlessly pulls gas away from its orbiting partner. This stolen material doesn't just fall quietly onto the surface, it spirals inward at nearly the speed of light, forming a searingly hot accretion disk. The friction and gravitational energy released in this process can heat the gas to millions of degrees, causing it to blaze with intense X-ray radiation. These systems are known as X-ray binaries, and they are scattered throughout the disks and halos of galaxies by the billions. Each one is a miniature, stellar-scale version of the awesome power of a supermassive black hole AGN. Individually, they are far less powerful, but their sheer numbers make them a formidable collective force. When astronomers began to inventory these systems and model their combined output, they ran headlong into the conundrum. Our best models of how galaxies form and evolve, which include sophisticated calculations of how many binary systems should exist and how active they should be, consistently predict a lower total X-ray luminosity than what we actually observe. The real universe appears to be significantly brighter in stellar X-rays than our theories say it should be. It's as if we've carefully calculated how many campfires there are in a national park, only to look at an infrared satellite image and see a glow that suggests twice as many fires are actually burning. This discrepancy points to a fundamental gap in our understanding of stellar astrophysics itself. Perhaps we are underestimating how efficient these binary systems are at converting gravitational energy into X-rays. Maybe the accretion disks are more stable or reach higher temperatures than our physics models predict. Another possibility is that we are grossly underestimating the total number of these systems, especially the older populations that have drifted into the dim outskirts of galaxies. There could be a vast, unseen reservoir of faint X-ray binaries, their combined murmur adding up to a significant portion of the background we detect. This conundrum forces us to re-examine the life cycles of stars, the complex physics of binary interactions, and the very population census of our own cosmic neighborhood. The answer to a universal mystery might be hiding in the intricate dynamics of common star systems, reminding us that sometimes the most profound secrets are not found in the most exotic places, but in the seemingly ordinary details we have yet to fully understand. Yet even with the combined might of stars and black holes, both hidden and visible, some astronomers believe we may still be missing a crucial piece of the puzzle, one that points to a component of the universe far more exotic and mysterious than anything we have discussed so far. This leads us to one of the most tantalizing and profound possibilities in all of modern cosmology, the dark matter connection. We have long known that the universe is primarily made of stuff we cannot see. Ordinary matter, the atoms that form everything from galaxies to human beings, accounts for a mere 5% of the cosmos. About 27% is the enigmatic force known as dark matter, an invisible substance that does not emit, absorb, or reflect any light, yet whose gravitational pull is the cosmic glue holding galaxies together. We know it's there because we can see its gravitational effects, but we have no idea what it is actually made of. This brings us to a revolutionary and thrilling idea. What if dark matter isn't completely dark in every sense? What if, under certain conditions, it can interact with itself? Many of the leading theoretical models propose that dark matter consists of a hypothetical class of particles known as weakly interacting massive particles, or WIMP. The name itself tells their story. They are thought to have mass, thus exerting gravity, and they interact via the weak nuclear force and gravity alone, making them incredibly difficult to detect. But here is the breathtaking part of the theory. In some models, when two WIMP collide, they could annihilate each other in a spectacular burst of energy, converting their mass directly into other particles, including gamma rays, neutrinos, and crucially, X-rays. Alternatively, a single, unstable dark matter particle could spontaneously decay, releasing a similar shower of radiation. This means that the very substance shaping the cosmos on its grandest scales could be faintly glowing in a light we are only just learning to see. The immense gravitational wells of galaxies and clusters, which are saturated with dark matter, could be subtle factories of high-energy photons. If this process is happening everywhere dark matter is concentrated, then its collective, universe-wide signal could be contributing to that very same, all-pervasive cosmic X-ray background we've been trying to explain. It's a concept that merges two of astronomy's greatest mysteries into one elegant, albeit unproven, solution. The unexplained glow we detect might be the faint, ghostly echo of the universe's hidden skeleton, slowly dissolving into light. The hunt for this signal is not a search for a random spike of energy. It is a meticulous forensic analysis looking for a very specific spectral signature. Astronomers aren't just looking for any X-ray. They are searching for a mysterious, faint line at a very specific energy of 3.5 kiloelectronvolts that has been detected emanating from the hearts of dozens of galaxies and clusters. This line has no obvious explanation from known atomic physics. It doesn't match the emission lines of any known element. It is an anomaly, and to many, it represents the most promising and controversial hint of dark matter decay we have ever seen. The excitement comes from the fact that if this line is indeed the signature of a dark matter particle, its energy would correspond to a particle with a specific mass, finally giving a concrete identity to the invisible majority of our universe. However, extraordinary claims require extraordinary evidence, and this one remains fiercely debated. Skeptics point out that the line could also be produced by more mundane, though poorly understood, processes involving potassium or chlorine ions in hot plasma. The problem is that our current instruments, as advanced as they are, lack the spectral resolution to definitively distinguish between these possibilities. The signal is right at the edge of what we can detect, sitting in a frustrating twilight zone between a monumental discovery and a potential calibration error. This is why the dark matter explanation remains one of the most exciting what-if scenarios in science. It represents a breathtaking possibility that by studying the oldest light in the universe, we might finally be staring directly at the true nature of the cosmos's most dominant, yet most elusive component. This leads us to perhaps the most ambitious and sweeping theory of all, one that seeks to connect the faint glow not to individual objects, but to the very architecture of the cosmos itself. We are now venturing into the realm of the cosmic web's X-ray signature. To understand this, we need to shift our perspective from looking at the universe's inhabitants to studying its infrastructure. For decades, cosmological simulations have predicted that the universe isn't just a random scattering of galaxies. Instead, under the relentless pull of gravity, all the matter in the cosmos has organized itself into a vast, intricate network, a great cosmic web. This web is made of dense knots where galaxy clusters reside, connected by long, thin filaments of gas and dark matter, with enormous, empty voids stretching between them. This isn't just a theoretical concept. We have actually mapped this large-scale structure by painstakingly plotting the positions of millions of galaxies. The resulting three-dimensional maps reveal this stunning web-like pattern, a fundamental blueprint for how matter is distributed across the universe. And according to the models, those filaments, the threads that stitch the cosmos together, should be filled with the elusive warm-hot intergalactic medium, the WIM. This isn't just warm gas, it's a plasma heated to millions of degrees by the tremendous shock waves generated as matter flows from the voids into the filaments and then into the clusters. A gas that hot should be shining brightly in X-rays. Therefore, the cosmic web itself, this magnificent skeleton of creation, should be faintly glowing. Theoretically, the combined X-ray light from this vast network of hot filaments could be a significant and fundamental component of the diffuse background we detect. The challenge, however, is that this signal is unimaginably faint. We are not trying to photograph a bright, defined object. We are attempting to detect the soft, almost imperceptible glow from the most diffuse and expansive structures in the universe. It's the difference between trying to photograph a lit light bulb in a dark room and trying to photograph the faint, ambient glow of all the light pollution from a distant city reflected off a high, thin cloud on a moonless night. Our current X-ray telescopes, as powerful as they are, simply weren't built with the sensitivity to see this. The signal from the web is drowned out by the brighter X-ray sources embedded within it, like trying to hear a whisper in a crowded, noisy room. To have any hope of success, astronomers have had to employ incredibly clever and indirect techniques. One of the most promising methods is not to look for the emission from the filaments directly, but to search for its absorption. This involves using the brightest X-ray flashlights in the universe, distant quasars, as backlights. As the intense X-ray light from a quasar travels for billions of years to reach us, it passes through these intergalactic filaments. The superheated gas within the filaments contains highly ionized atoms of heavy elements like oxygen and neon. These ions can absorb very specific wavelengths of the quasar's light, creating tiny, telltale dips in its spectrum. It's akin to figuring out what a distant, foggy object is made of by analyzing the specific colors of a bright light shining from behind it. Finding these absorption lines is like finding the fingerprint of the cosmic web itself, confirming that the whim is indeed there, hiding in the filaments. A handful of tantalizing detections using this method have been reported, providing some of the strongest evidence yet that the missing baryons are in this web of hot gas. But to move from detecting a few fingerprints to actually seeing the web's own glow requires a monumental leap in technology. This is the driving force behind concepts for next-generation X-ray observatories like the proposed Lynx or Athena missions. These telescopes would have vastly larger collecting areas, imagine mirrors, not with the surface area of a desk but of a tennis court, and revolutionary spectral resolution. They would be designed specifically to perform a kind of cosmic tomography, building up a three-dimensional picture of this faint X-ray emission, and finally revealing the hidden rivers of hot gas that flow between the islands of galaxies. Successfully observing this direct emission would be a transformative achievement for cosmology. It would do more than just solve the missing baryon problem. It would allow us to study the dynamics of the cosmic web itself. We could track how gas flows into and out of clusters, measure the strength of the shock waves that heat it, and ultimately understand how the universe funnels raw material to the galaxies within it, fueling the birth of stars and the growth of black holes. We would be witnessing the universe's circulatory system in action. The cosmic X-ray background, therefore, might hold within its uniform glow the faint but discernible map of creation's grand design, a direct echo of the gravitational forces that have shaped everything we see. But as we peel back the layers of this cosmic onion, we uncover a puzzle within a puzzle, a discrepancy that pushes the very limits of known physics. This brings us to the enigma of the high-energy excess. When astronomers meticulously dissect the cosmic X-ray background, breaking it down by energy level, they find that the various sources we've identified, the active galactic nuclei, the galaxy clusters, the X-ray binaries, form a convincing patchwork that explains most of the glow, but with one glaring and persistent exception. At the very highest energies, above 20 kiloelectronvolts, the models fall apart. There is a stubborn and significant surplus of hard X-rays that simply cannot be accounted for by any known population of celestial objects. It's as if you carefully calculated the combined output of every known power plant on Earth, only to discover that the grid is still drawing power from a massive, hidden generator operating in plain sight. This high-energy excess is particularly baffling because of what it implies about its source. X-ray photons at these energies are incredibly powerful. To produce them requires processes of immense violence and power particles being accelerated to near light speed, temperatures reaching billions of degrees, or matter being subjected to gravitational forces beyond comprehension. The usual suspects, like the accretion disks around supermassive black holes, do produce hard X-rays, but when we add up all their potential contributions, we are still left with a glaring shortfall. This forces us to consider that the answer might lie not in more of the same, but in something entirely new, something exotic that has, until now, remained completely hidden from our view. One of the most fascinating possibilities involves a ghost from the universe's very first moment, primordial black holes, theorized to have formed not from the death of stars, but from the extreme densities of the Big Bang itself. These black holes could be almost any size. Some might be as small as an asteroid, yet contain the mass of a mountain. A vast, hidden population of these ancient objects could be drifting through the universe, mostly invisible. But if they were to pass through a dense cloud of gas or even a star, their immense gravity could pull material into a miniature, ultra-hot accretion disk. While a single one would be faint, the combined emission from trillions upon trillions of them, scattered throughout every galaxy and in the vast emptiness between them, could generate precisely the type of diffuse, high-energy X-ray glow that we cannot otherwise explain. They would be the universe's ultimate stealth fleet, their collective engine hum forming a background chorus we are only just beginning to hear. Another, even more profound explanation points back to the dark matter mystery, but in a more extreme form. Perhaps the standard WIMP models are not the whole story. What if dark matter consists of super-heavy particles with masses far greater than any particle predicted by standard theories? These hypothetical particles, with names like WIMP-zillas, could be so massive that their decay would be a rare event, but when it does occur, it would release a tremendous burst of energy, including a shower of high-energy X-ray photons. If this decay is happening continuously across the entire universe, within every galaxy and every cluster, it would produce a perfectly uniform, high-energy background that would be nearly impossible to trace back to any single location. The excess we see could be the final, fading signal of the universe's dominant substance slowly disintegrating over trillions of years. Beyond these exotic particle ideas, the high-energy excess forces us to confront an even more radical possibility, that we are witnessing the signature of entirely new physical processes. The laws of physics, as we currently understand them, are incredibly successful at explaining the universe within a certain domain. But at the extreme energies required to produce this signal, we might be brushing up against the edges of our knowledge. Could it be evidence of extraspatial dimensions as predicted by string theory, where the fundamental forces of nature behave differently at tiny scales? Or perhaps it is a sign of actions, another hypothetical dark matter particle, converting into X-rays in the powerful magnetic fields that surround galaxy clusters. Each possibility opens a door to a universe far stranger and more wonderful than we had previously imagined. Resolving this mystery is not just an academic exercise, it is a fundamental test of our understanding of reality. The high-energy excess is a direct challenge, a piece of data that refuses to fit neatly into our existing cosmic models. It is the astronomical equivalent of an anomaly in a grand experiment, and history has shown us that it is often the anomalies that lead to the greatest leaps in understanding. The mission to explain this excess is already driving the design of a new generation of hard X-ray and gamma-ray telescopes, instruments that will peer deeper into this energetic realm than ever before, hoping to catch a glimpse of whatever incredible engine is powering this mysterious and pervasive cosmic light. This idea that the cosmic X-ray background is a static, unchanging tapestry of ancient light has been a foundational assumption for decades. It makes intuitive sense. If this glow is the combined light of countless distant sources, its signal should be as stable and eternal as the universe itself on a human timescale, a perfect average of cosmic history. But what if that assumption is wrong? This brings us to one of the most perplexing and recent twists in our investigation, the time variability puzzle. Imagine carefully observing a vast, seemingly motionless forest from a great distance. Over years, its overall appearance doesn't change. But then, with a more sensitive instrument, you notice something astonishing. Tiny, subtle flickers are happening within that uniform canopy. Not in one spot, but scattered throughout, this revelation shatters the illusion of a static scene, proving there is dynamic life within it. This is precisely what astronomers began to see in the CXB. The first hints of this variability were subtle, buried in the vast datasets from observatories like Chandra and XMM Newton. Scientists were meticulously comparing observations of the same patch of sky taken months or even years apart. Their goal was to find new, transient X-ray sources that flared up and faded, like supernova or tidal disruption events where a star is shredded by a black hole. But in the process, they noticed something far more bizarre. The overall, diffuse background glow itself seemed to be shifting in intensity and not in a uniform way. Certain regions appeared to brighten or dim ever so slightly over time. The changes were minuscule, often at the very limit of what these powerful telescopes could detect, but they were statistically significant. This was not supposed to happen. A truly cosmological background, a fossil imprint from the early universe, should be constant. This faint flickering suggested that a portion of the glow must be coming from a population of sources that are much closer to us and capable of change. This discovery immediately narrows the list of suspects. It effectively rules out the warm-hot intergalactic medium as the sole culprit. The vast filaments of the cosmic web are so enormous and diffuse that they cannot vary on human timescales. Their light travel time alone is measured in hundreds of millions of years. The flickering also can't be coming from the most distant quasars, whose light has been traveling for over 12 billion years. Their individual variations would be completely averaged out into a steady hum by the time it reached us. The variability points a decisive finger at a population of sources within our own cosmological backyard, relatively speaking objects within our local universe that are dynamic on timescales of months or years. So, what could these hidden, variable contributors be? The prime suspects are once again active galactic nuclei, but with a specific twist. We already know that the X-ray output from a feeding supermassive black hole is incredibly volatile. Their luminosity can swing wildly as the rate of infalling matter changes. If a significant number of the AGN contributing to the background are relatively nearby and obscured by thick clouds of gas, a change in that obscuring material could also cause a detectable shift in their overall output. A dense cloud moving out of the line of sight would make the black hole suddenly appear brighter, while a cloud drifting into view would dim it. This dance of shadows and light from thousands of such hidden monsters could create the faint, shimmering effect we detect in the integrated background light. But there's an even more intriguing and less understood possibility: a vast population of incredibly faint, stellar-scale objects within our own galaxy. We've discussed how X-ray binaries can vary, but what if there are millions of even smaller, quieter systems? Consider cataclysmic variables, binary systems where a white dwarf star is steadily pulling material from a companion. These systems can have regular outbursts, and their combined, faint X-ray emission could be woven into the fabric of what we perceive as the diffuse background. If a large number of them were to go into outburst around the same time in a particular region of the sky, they could cause the subtle fluctuations we observe. This would mean that a portion of the cosmic X-ray background isn't cosmic at all. It's galactic, a foreground fog of countless faint, twinkling stars that we have yet to resolve individually. Unraveling this puzzle is a monumental technical challenge. It requires painstakingly comparing vast datasets across different epochs, a process vulnerable to instrumental effects and subtle calibration differences. Confirming it will likely require a future observatory dedicated to making an ultra-precise, all-sky map of the X-ray sky, and then repeating that map years later to look for changes. The existence of time variability fundamentally changes the nature of the cosmic X-ray background. It is not a frozen fossil. It is a living entity, a dynamic canvas that continues to evolve and change, reminding us that even the deepest, most fundamental layers of our universe are still actively writing their story. This faint flickering is a message, a clue that the final answer to this 60-year mystery might be hiding not only in the depths of space, but in the dimension of time itself. Yet this faint, shimmering variability in the present-day universe forces our investigation to pivot and peer back across the deepest gulfs of time, to an era when the first monstrous engines of creation flickered to life. This brings us to a mystery that lies at the very frontier of cosmology itself, the first black holes problem. Woven into the very fabric of the cosmic X-ray background could be the faint, diluted echo of the universe's very first supermassive black holes, entities so ancient and powerful that their origins defy our current understanding of physics. To find them, we must journey back to the cosmic dawn, a period just a few 100 million years after the Big Bang, when the first stars and galaxies were beginning to illuminate the darkness. The problem is one of sheer, breathtaking scale. We have discovered quasars, supermassive black holes actively devouring matter that existed when the universe was less than 700 million years old. These are not tiny seeds, they are already behemoths weighing over 1 billion times the mass of our Sun. This presents a monumental puzzle for astrophysicists. How did these black holes grow so massive, so quickly? There simply isn't enough time in the early universe for a humble stellar mass black hole, the remnant of a single star, to gorge itself and grow to such an immense size through normal accretion. It would be like expecting a newborn baby to grow to the size of a blue whale in just a few months. The math simply doesn't work. This paradox has led to the theory of direct collapse black holes. Imagine a scenario in the primordial universe before the first stars had fully formed. A massive cloud of pristine hydrogen gas begins to collapse under its own gravity. But without heavier elements to help it cool and fragment, it doesn't break apart into many smaller stars. Instead, the entire gigantic cloud, weighing millions of solar masses, collapses directly into a single massive black hole seed. This is not a star that died, it is a monster born whole from the cosmic womb. These primordial giants would have had a tremendous head start, allowing them to rapidly grow into the supermassive black holes we see powering those early quasars. Theoretically, the universe should be filled with the remnants of these first-generation black holes, and their collective feeding activity should have flooded the early universe with X-ray radiation. This is where the cosmic X-ray background becomes our only time machine. The light from those first, incredibly distant black holes has been traveling for over 13 billion years to reach us. During its journey, the expansion of the universe has stretched the wavelengths of that light, shifting it from high-energy X-rays into lower-energy parts of the spectrum. This means the specific contribution from the very first black holes is not something we can easily isolate with our current instruments. It is thoroughly mixed into the overall background hum. Disentangling their specific signal is like trying to identify the individual voices of a few specific singers in a recording of a massive choir from a mile away, after the recording has been heavily filtered and compressed. Their unique song is in there, but extracting it is a formidable challenge. The hunt for this signal is driving some of the most advanced computer simulations in the world. Cosmologists are creating virtual universes, seeding them with different populations of these first black holes. Some formed from direct collapse, others from the first generations of massive stars, and then calculating what the combined X-ray output would look like after 13 billion years of cosmic evolution. They then compare this simulated background to the one we actually observe. The subtle differences in the spectrum's shape and intensity hold the key. A background that has a stronger component from very high energy sources might point to a universe filled with direct collapse monsters, while a different signature might suggest a dominance of smaller stellar-born seeds. Furthermore, the light from these first black holes didn't just travel unimpeded, it interacted with the infant universe itself. Those early X-rays were the first major source of energy that began to heat and re-ionize the neutral hydrogen gas that filled the cosmos after the Big Bang. This process, called re-ionization, was a pivotal epoch that made the universe transparent to light as we see it today. The characteristics of the cosmic X-ray background are therefore intimately tied to this transformation. By studying the background, we are indirectly studying how and when this fundamental phase change occurred, and thus the properties of the very engines that powered it. Unlocking this mystery is the primary goal of a new generation of space observatories. Missions like the upcoming European New Athena telescope or the conceived Lynx mission will have the spectral resolution to begin to tease apart these different components. They won't see individual first black holes, but they will be able to detect the chemical fingerprints their radiation left on the very fabric of space-time. It is a forensic investigation on a cosmic scale. The cosmic X-ray background is not just a glow, it is a palimpsest, a layered historical document. Written over in later eras by newer sources, the faint, underlying text from the universe's first chapter is still there, waiting for us to develop the tools to read it. Solving the first black holes problem would do more than just explain a component of the background. It would reveal the origin story of the most powerful objects in the cosmos and rewrite our understanding of how the universe woke up from its dark ages. Yet this grand puzzle of universal background radiation presents a unique and deeply personal mystery when we turn our gaze much closer to home. If the cosmic X-ray background is truly the collective glow of countless individual sources spread across the universe, then our own cosmic neighborhood, the Milky Way galaxy and its nearby companions, should be contributing their fair share to this immense light show. But when astronomers point their most sensitive instruments at these local galaxies, they are met with a confounding discrepancy. Our own galaxy and its closest relatives appear to be significantly underluminous in X-rays compared to what the models predict they should be emitting. It's as if you calculated the total light output from every house in a vast city, only to discover that your own street is oddly and inexplicably dark. This missing galactic emission is a profound paradox that strikes at the heart of our understanding of how galaxies evolve. The Milky Way is a perfectly normal, large spiral galaxy, teeming with all the known ingredients that should produce X-rays. We have a supermassive black hole at its heart, Sagittarius a star, though it is currently in a quiet phase. Our galaxy is filled with X-ray binaries, supernova remnants, and vast bubbles of hot gas blown out by stellar winds. We can see them, we can count them, and we can measure their individual brightness. Yet when we add it all up, the total X-ray luminosity of the Milky Way falls short of what we would expect based on its mass, its star formation rate, and its overall similarity to other galaxies that contribute to the distant background glow. The same is true for many of our galactic neighbors, like the Andromeda galaxy. They simply aren't as bright in X-rays as the cosmic average seems to demand. One of the most compelling explanations for this local dimness is a simple matter of perspective and observational bias. Think of it like trying to study the structure of a vast forest while you are standing deep inside it. From your position on the forest floor, surrounded by trees, it is incredibly difficult to see the overall shape of the woods or to get an accurate count of all the trees. You have a clear view of the individual trunks immediately around you, but the canopy above blocks your view of the rest. This is precisely our challenge within the Milky Way. Our solar system is embedded within the galaxy's dusty disk. This means that when we try to observe X-ray sources on the far side of the galaxy, their light is heavily absorbed by the immense clouds of gas and dust that lie between us and them. We could be missing a significant population of faint X-ray sources simply because they are hidden behind these cosmic curtains. This observational hurdle is known as the confusion limit. In the crowded central regions of our galaxy, the sheer density of stars and potential X-ray emitters is so high that our telescopes cannot resolve them all into distinct points of light. Their signals blur together into an unresolved fog that we might mistake for a truly diffuse background or simply fail to account for in our tallies. It is entirely possible that our own galaxy is actually teeming with a vast population of very faint X-ray sources, old neutron stars, quiet binary systems, and dim stellar remnants that are simply too faint and too crowded for our current instruments to individually pick out. Their collective murmur could represent the missing X-ray flux, a hidden chorus of stellar engines whose combined song we are only just beginning to hear. Beyond these observational challenges, there is a more fascinating possibility rooted in the very nature of cosmic time. Galaxies are not static, they evolve. The Milky Way is a mature, middle-aged galaxy. Its frenetic period of rapid star formation and frequent supernova is largely in the past. This is crucial because stellar X-ray sources, particularly the powerful X-ray binaries, are often associated with youthful stellar populations. They are the products of massive, short-lived stars that explode and leave behind dense cores. A galaxy in its rambunctious youth, brimming with hot, young stars and constant supernova explosions, would be an X-ray powerhouse. In contrast, our settled galactic neighborhood is comparatively quiet. The unresolved cosmic X-ray background, however, is an average taken over the entire observable universe and across billions of years of cosmic history. It includes the light from countless galaxies that are currently in their most violent and energetic phases of life. Our local dimness, therefore, might not be an anomaly at all, but simply a reflection of our galactic maturity. We are living in a relatively peaceful era in a relatively peaceful part of the universe, quietly contributing less to the cosmic din than our more tempestuous cousins. This leads to another intriguing idea, that the Milky Way might be fundamentally different in a way we haven't fully appreciated. Perhaps the precise structure of a galaxy's halo, the amount of hot gas it can retain, or the specific history of mergers that built it play a decisive role in its X-ray output. Our galaxy has a specific mass, a specific magnetic field structure, and a specific history of consuming smaller dwarf galaxies. This unique combination of traits might have created an environment that is less efficient at producing or retaining the types of systems that generate copious X-rays. We might be a perfectly normal galaxy, but normal encompasses a wide range of behaviors, and we simply fall on the quieter end of the X-ray spectrum. Solving the mystery of our missing galactic sources is more than an academic exercise. It forces us to question whether we truly understand what normal is for a galaxy, reminding us that sometimes the most familiar places can hold the most surprising secrets. This brings us to a controversy that strikes at the very core of our cosmological models, a debate that hinges on a single, profound question. Is the cosmic X-ray background truly and perfectly uniform? We now enter the anisotropy controversy. The term isotropic has been our guiding principle, the foundational assumption that this glow is the same in every direction, a universal constant that confirms the grand cosmological principle, the idea that on the largest scales the universe is homogeneous and has no preferred direction. But what if that's not entirely true? What if, buried within that seemingly smooth signal, are tiny, subtle variations, tiny ripples that point to a lumpy, uneven distribution of its sources? Finding these ripples, known as anisotropies, would be a revolution. Not finding them where we expect to would be a crisis. The technical challenge of this search cannot be overstated. We are not looking for obvious bright spots or dark patches. We are hunting for fluctuations in the background glow at a level of 1% or even less. It is the astronomical equivalent of trying to measure the microscopic texture on the surface of a perfectly smooth sheet of glass by only looking at the way light reflects off it from a mile away. The signal is impossibly faint, and it is buried under a mountain of noise. This noise isn't just instrumental hiss from our telescopes, it comes from our own galactic neighborhood. The Milky Way itself emits a foreground fog of X-rays from its own hot gas and stellar sources, and this local emission is decidedly not uniform. Before you can even hope to see the subtle wrinkles in the distant cosmic tapestry, you must first perfectly subtract this brilliant, complicated foreground veil, a process that is as much an art as it is a science. This immense difficulty has split the scientific community into two camps, each armed with data from the world's most powerful observatories. One group, analyzing incredibly deep exposures from the Chandra X-ray Observatory, has reported the detection of significant fluctuations at small angular scales. They argue that these tiny bumps and wiggles in the signal are the long-sought statistical signature of the cosmic web's filamentary structure. They believe they are seeing the faint, clumped glow of the warm, hot intergalactic medium, the hidden baryons, finally revealing their distribution. This would be a monumental confirmation, not only of the missing matter's location, but of our entire theory of how large-scale structure forms under gravity. The other camp, often working with data from XMM Newton or other instruments, has looked for the same signal and found nothing but profound smoothness. They argue that the reported fluctuations are not cosmological at all, but are instead artifacts of imperfect foreground subtraction or the intrinsic variability of faint, unresolved sources within our own galaxy that haven't been fully accounted for. They maintain that the background, at the limits of our current ability to measure it, remains stubbornly isotropic. This disagreement is not merely academic. It is a fundamental clash over the interpretation of data at the very edge of detection, where the line between a revolutionary discovery and a systematic error is vanishingly thin. The implications of this debate are staggering. If the anisotropies are real, they provide a direct window into the distribution of matter in the universe. By studying the pattern of these fluctuations, their size and amplitude, cosmologists could potentially measure the mass of the neutrino, pin down the exact properties of dark matter, and trace the gravitational scaffolding that dictated where galaxies would eventually form. It would be a new and powerful probe of the cosmos's invisible architecture. Conversely, if the background is confirmed to be perfectly smooth at these small scales, it would trigger a profound cosmological crisis. Our standard model of the universe, lambda cold dark matter, confidently predicts that the distribution of matter, and therefore the X-ray sources that trace it, should be clumpy. A complete lack of anisotropy would mean that something is terribly wrong. It could imply that the sources of the background are far more numerous and evenly distributed than any model predicts, perhaps requiring a radical new population of objects we haven't even conceived of yet. Or, even more dramatically, it could suggest that our understanding of gravity itself is incomplete on the largest scales, challenging the very foundation upon which modern cosmology is built. The anisotropy controversy is therefore far more than a technical argument. It is a high-stakes battle over the true nature of the universe, fought in the faintest of whispers against an overwhelming sea of noise. If you were to ask an astronomer to describe the unique sound of the universe in X-ray light, they wouldn't point to a single, pure note. Instead, they would play you a complex chord, a layered harmony of countless different instruments all playing at once. This is the spectral shape riddle of the cosmic X-ray background. Every type of cosmic object emits X-rays with a distinct spectral signature, a unique fingerprint that describes how its intensity changes across different energy levels. A supermassive black hole's accretion disk produces a very different pattern of light than the hot gas in a galaxy cluster or a stellar binary system. The grand mystery is that when we finally measured the overall spectrum of the CXB, its shape didn't match any one of these individual sources. It was something entirely new, a blended recipe that no single ingredient could explain. Think of it like a master chef presenting you with a completely unknown, exquisite dish and challenging you to reverse engineer the recipe solely by its taste. You can identify hints of familiar flavors, a note of black hole here, a whisper of hot gas there, but the overall profile is unique and complex. Reproducing that exact flavor in your own kitchen requires not only identifying every single ingredient but also knowing their precise proportions and how they were combined. For cosmologists, the spectral shape of the background is that unknown dish, and for decades their attempts to cook up a model that matches it have consistently fallen short. The challenge is to take every known population of X-ray source, the bright quasars, the obscured AGN, the galaxy clusters, the X-ray binaries, calculate their individual spectral contributions, and then mix them together in just the right amounts to perfectly recreate the smooth, observed curve of the CXB. This has proven to be an extraordinarily difficult balancing act. Early models that relied too heavily on the unobscured, powerful active galactic nuclei produced a spectrum that was too hard, meaning it had too much high-energy light. Conversely, models that emphasized the softer emission from hot gas in galaxy clusters failed to account for the higher energy tail. The only way to get the shape right is to invoke a very specific and somewhat contrived mixture of sources. You need a dominant population of heavily obscured black holes to provide the soft, lower energy component, but you also need just the right number of brighter, harder sources to pump in the higher energy photons. Furthermore, you must distribute these sources perfectly across cosmic history, because the expansion of the universe stretches the light from more distant objects, shifting their spectral signatures to lower energies. The problem is that this required mixture often conflicts with what we actually observe in the local universe. Our census of nearby galaxies suggests there might not be enough obscured AGN to provide the necessary soft emission, or that the accretion rates onto black holes in the early universe might need to be different than we currently believe. It forces theorists into a corner where they must either propose the existence of entirely new classes of sources we haven't found yet, or admit that we may not fully understand the physics of accretion and X-ray production in the environments that dominated the early cosmos. The spectral shape is a ruthless arbiter of truth. It doesn't care for elegant theories, only for the cold, hard data of the final combined light. This riddle is more than just a technical detail. It is a fundamental constraint on the entire history of the universe. The precise shape of the spectrum holds within it clues about the evolution of cosmic structures, the growth of black holes, and the life cycle of stars across billions of years. Successfully matching it would mean that our inventory of the cosmos and our understanding of its energetic processes are essentially complete. The continued failure to do so is a humbling reminder that our picture of the high-energy universe is still missing crucial pieces, and that the final answer will likely require a deeper, more nuanced understanding of how all these incredible engines work together to compose the universe's enduring, energetic symphony. This relentless pursuit to resolve the cosmic X-ray background into its individual components is one of the great detective stories in modern astronomy, a mission that has driven the design of our most powerful space observatories. The core idea was beautifully simple. If this pervasive glow truly comes from countless point sources, then a telescope with enough sensitivity and angular resolution should be able to see them. It should be able to shift our perception from a uniform haze to a glittering sea of distinct points of light, much like the moment your eyes adjust to a dark night sky, transforming a milky band into countless individual stars. This was the promise of NASA Chandra X-ray Observatory and the European Space Agency's XMM Newton, two magnificent instruments launched around the turn of the millennium. Their goal was not just to see deeper, but to finally complete the cosmic census and solve the mystery. The results from their deepest surveys, like the Chandra Deep Field South, were nothing short of revolutionary. Peering at a single, seemingly blank patch of sky for weeks on end, these telescopes did what they were designed to do. They resolved a huge portion of the background. They revealed thousands upon thousands of previously hidden active galactic nuclei, turning a faint glow into a brilliant, pointillist masterpiece of supermassive black holes. It was a monumental achievement that confirmed the foundational hypothesis: a significant part of the CXB does indeed come from discrete sources. But in doing so, these incredible machines unveiled a deeper, more perplexing layer to the mystery. Even after adding up the light from every single source they could possibly identify, a stubborn fraction of the background remained, somewhere between 20 and 30% of the total X-ray flux simply refused to be resolved into a distinct point. It was as if a master painter had filled a canvas with millions of detailed figures, yet a fundamental part of the shading and light continued to emanate from the canvas itself. This is the resolution paradox. The better our telescopes become, the more sources we find, yet a portion of the background remains eternally just beyond our grasp, a diffuse whisper that refuses to be pinned down. This finding forces a critical conclusion. The missing sources cannot simply be fainter versions of the active galactic nuclei we already know. If they were, our deepest observations would have found them. Instead, they must be fundamentally different. They must be sources that are so incredibly faint or so numerous that they blend together into an indistinguishable haze, or so diffuse that they have no central point to resolve. This paradox points directly to a population of objects that are either intrinsically low luminosity or so deeply shrouded in gas and dust that their highest energy light is completely absorbed, leaving only a soft, spread-out signature. The implications of this unresolved fraction are profound. It suggests that our inventory of the cosmos, even after Chandra and XMM Newton, is still incomplete. We are missing an entire class of cosmic engine. The leading candidate for this missing population is the long-theorized legion of Compton-thick active galactic nuclei, black holes so heavily veiled that even their faint, leaked radiation is too diffuse to be seen as a distinct point. But other fascinating possibilities exist. It could be the collective emission from truly vast numbers of stellar mass objects, black holes, and neutron stars in binary systems that are too faint individually to detect across intergalactic distances, but whose combined murmur creates a significant background hum. Or it could be the signature of the warm, hot intergalactic medium itself, the hot gas in the cosmic web filaments, which is, by its very nature, extended and diffuse rather than point-like. This unresolved glow is therefore a beacon guiding the design of the next generation of X-ray telescopes. Missions like the proposed Lynx Observatory or ESA's new Athena are being conceived with one primary goal: to push beyond this current limit. They will need exponentially greater sensitivity to detect those incredibly faint point sources, and vastly improved spectral resolution to tease apart the true nature of the diffuse component. The resolution paradox is not a failure of our current technology. It is a signpost. It tells us that the final answer to the 60-year mystery of the cosmic X-ray background lies in a realm of faintness and obscurity that we are only just beginning to explore, a hidden universe waiting for its moment to be seen. While the titanic power of black holes and the quiet hum of stars are key players, many astronomers believe the true resolution to the cosmic X-ray mystery lies in something far more vast and elusive, woven into the very fabric of the cosmos itself. This brings us to a leading hypothesis, one that connects the background glow to the universe's hidden architecture, the warm, hot intergalactic medium, or the WIM. For decades, our maps of the universe were like those of early explorers, charting only the islands and continents, the bright galaxies and clusters, while completely missing the ocean that surrounds them. The WIM is that ocean, a vast, diffuse web of superheated gas that resides in the immense filaments of the cosmic web, the largest structures in the universe. This isn't just warm gas, it's a searing plasma, heated to temperatures between 100,000 and 10 million degrees. It was cooked to these incredible temperatures by the most violent processes in the universe's history. As matter collapsed under gravity to form the great cosmic web, it didn't fall gently. It slammed into itself at colossal speeds, creating immense shock waves that traveled through the primordial gas, heating it to these tremendous temperatures. And according to the fundamental models of cosmology, this WIM is where the universe hid its missing ordinary matter. The math from the Big Bang tells us how much baryonic matter should exist, but for years we could only account for about half of it in stars, galaxies, and cold gas. The WIM is the prime suspect for that missing half, the hidden repository of the universe's atomic building blocks. A gas this hot behaves in a very specific way. It doesn't glow in visible light. Its atoms are moving far too fast and are stripped of their electrons. Instead, it shines through high-energy processes. The primary mechanism is thermal Bremsstrahlung, that same breaking radiation we see in galaxy clusters, but here it's happening in a far more diffuse environment. Free electrons zipping through the plasma are deflected by the positively charged atomic nuclei, and with each tiny course correction, they release a small amount of energy as an X-ray photon. Envision a vast, invisible network of wires, each one humming with a faint, energetic charge. Across the unimaginable volume of the cosmic web, trillions upon trillions of these tiny interactions are happening every second, and their collective, universe-wide output could very well be a major component of that mysterious, uniform X-ray background we detect. It would be the faint, steady glow of the universe's hidden skeleton. The challenge, of course, is that this signal is almost impossibly weak. We are not trying to photograph a bright object. We are attempting to see the soft, ambient radiance from the most diffuse structures in existence. It's the astronomical equivalent of trying to see the heat haze rising from a road on the horizon from 100 miles away. Our current telescopes, like Chandra and XMM Newton, were marvels of their time, but they simply don't have the sheer light-gathering power or the spectral resolution to isolate this faint whisper from the brighter X-ray sources embedded within the web. The signal from the WIM is drowned out, lost in the cosmic static. This is why astronomers have had to become incredibly clever detectives, employing indirect methods to hunt for the WIM fingerprints. The most successful technique so far hasn't been to look for its emission, but for its absorption. This involves using the brightest beacons in the universe, distant quasars, as cosmic flashlights. As the intense X-ray light from a quasar travels for billions of years to reach our telescopes, its path takes it through these intergalactic filaments. The highly ionized atoms within the WIM, oxygen, neon, and other heavy elements are very picky eaters. They absorb very specific, precise wavelengths of that quasar's light. By analyzing the quasar's spectrum with exquisite detail, astronomers can search for these tiny, telltale dips, these missing pieces of the light. Finding these absorption lines is like finding the signature of the cosmic web itself. It's proof that the WIM is there, hiding in the filaments, its presence revealed by the shadow it casts. A handful of these tantalizing detections have been made, providing some of the most compelling evidence that the missing baryons are indeed in this web of hot gas. But these are just fingerprints. The ultimate goal is to see the hand. We want to move from detecting a few scattered clues to actually mapping the glow of the web itself, to seeing its structure and understanding its properties. This monumental task is the primary driving force behind the next generation of X-ray observatories, missions that are currently on the drawing board. Concepts like the Lynx X-ray Observatory or the European Space Agency's new Athena mission are designed as universe-class detectives. They envision telescopes with mirrors that have dozens of times the collecting area of Chandra, and with spectral resolution so sharp they can distinguish the faintest of features. These future observatories won't just see a few points of light, they will perform a kind of cosmic tomography. By staring at deep fields for unprecedented lengths of time, they will build up a three-dimensional picture of this faint X-ray emission, allowing us to literally see the filamentary structure of the warm, hot intergalactic medium. They will measure its temperature, its density, and its chemical composition, finally answering the question of whether it holds the full amount of the universe's missing ordinary matter. Success wouldn't just solve a 60-year-old mystery about the X-ray background. It would complete our inventory of the atomic universe and allow us to study the dynamics of the cosmic web in action, watching how gas flows into galaxies to fuel the next generation of stars and black holes, revealing the circulatory system of the cosmos itself. So we've seen the individual suspects, from hidden black holes and hot gas to flickering stars and even dark matter. But how do we combine them all into a single, cohesive theory? This brings us to one of the most daunting and cerebral challenges in modern astrophysics, a digital detective story that unfolds not at a telescope but inside a supercomputer. This is the population synthesis challenge. Imagine you're given a vast, complex symphony to analyze. You can pick out the blaring trumpets of the quasars, the steady hum of the cellos from the galaxy clusters, and the faint, rhythmic tapping of the percussion from the stellar binaries. Your task is to take the sheet music for every known instrument and combine them in just the right proportions with the exact right timing to perfectly recreate the symphony you hear. That's precisely what astrophysicists are trying to do with the cosmic X-ray background. They are master composers using computer code instead of sheet music, attempting to synthesize the entire high-energy universe from its individual parts. This process is called cosmological population synthesis modeling. It's a breathtakingly ambitious endeavor that requires weaving together knowledge from almost every branch of astrophysics. The modelers start with our best understanding of how the universe itself evolved, the lambda-cold dark matter model, which charts the growth of structure from the smooth aftermath of the Big Bang to the great cosmic web we see today. Onto this expanding canvas, they must paint the life stories of every conceivable X-ray source. They code in the physics of how gas collapses to form the first stars and black holes. They program in the rules for how supermassive black holes grow, feast, and flicker over billions of years. They account for the birth, life, and violent deaths of binary star systems, modeling how they ignite as X-ray sources and then fade away. Every parameter, from the rate of star formation in a galaxy to the density of a dust cloud obscuring a black hole, must be included and given a value based on our best observations. The goal is deceptively simple. Run the simulation forward over 13.8 billion years of cosmic history. Add up all the X-ray light produced by every single object in the virtual universe, and then compare that final, combined spectrum to the one we actually observe from the real cosmic X-ray background. For decades, the result of this monumental computational effort has been a persistent, humbling failure. No matter how the theorists tweak the parameters, their synthetic universe consistently falls short. It's like our master composer has all the right instruments, but the resulting music is always missing a crucial section of the orchestra. The simulated background is either too bright at high energies and too dim at low energies, or its overall intensity is too weak, or it lacks the perfect uniformity we detect. The model simply cannot reproduce the exact smooth, specific spectral shape of the real thing with the ingredients we know about. These consistent failures are not a sign of a broken process, they are invaluable clues. They tell us with mathematical certainty that our inventory of the cosmos is incomplete. The universe is using instruments we haven't yet found or fully understood. So, what are the missing ingredients? Theorists are now exploring a fascinating menu of possibilities, each more compelling than the last. The prime suspect remains a vast, hidden population of heavily obscured active galactic nuclei, particularly those in the Compton-Thick regime. Our current surveys are heavily biased toward finding black holes that are easy to see. We may be missing an entire demographic of monsters that are shrouded in such thick cocoons of gas that they leak only a soft, diffuse glow, which could perfectly account for the unresolved portion of the background that has the spectral shape the models can't replicate. Another missing ingredient could be a much larger number of low-luminosity active galactic nuclei than we currently predict. Our models are often built on the brilliant, flashy quasars, but for every brilliant quasar, there might be 1,000 quieter, steadily feeding black holes that are too faint for us to easily detect individually. Their collective, steady hum could be a significant part of the background music. Beyond black holes, the models might be severely underestimating the contribution from stellar-scale objects. Could there be a vast, unseen population of faint white dwarfs, neutron stars, or even planetary nebulae in the halos of galaxies, whose combined X-ray output is greater than we ever imagined? Or perhaps the physics itself is wrong. Maybe our understanding of how accretion disks work, how they convert gravitational energy into X-rays, is incomplete. A slight miscalculation in the efficiency of this process, multiplied across billions of sources and billions of years, would throw off the entire synthetic symphony. The most radical potential ingredients are those that would rewrite the rules entirely. Could the synthesis models be failing because they don't include the decay of a certain type of dark matter particle? Or because they don't account for the collective emission from a sea of primordial black holes? The population synthesis challenge is therefore the grand unifier of all the other mysteries. It is the courtroom where every suspect, the hidden black holes, the missing galactic emission, the dark matter signal, must take the stand and prove it can account for the discrepancy. Each new observation, each deeper look into the universe, provides new data to constrain these models, forcing them to become more sophisticated and hopefully more accurate. The day a population synthesis model can finally, perfectly recreate the observed cosmic X-ray background will be a monumental milestone in science. It will mean we have truly solved the chorus, identified every last player in the cosmic orchestra, and finally understand the complete score of the high-energy universe. Yet for all our searching across the cosmic depths, one of the most perplexing obstacles in our quest to understand the background's origin comes from a source much closer to home, an unexpected form of pollution emanating from our own celestial neighborhood. This is the confounding problem of galactic contamination, a foreground fog of X-ray light generated within the Milky Way that subtly blends with and masks the truly extragalactic signal we are so desperate to isolate. Imagine trying to listen for a faint, distant symphony while standing right next to a rushing waterfall. The powerful, local noise drowns out the delicate music from afar. For astronomers, this waterfall is the vibrant X-ray activity of our own galaxy, and filtering out its roar to hear the cosmic whisper has become a scientific endeavor of immense complexity. One of the most surprising and recently discovered sources of this local interference comes from a process so mundane it's almost poetic. Deep within our solar system, a gentle but constant rain of particles from the sun, known as the solar wind, flows outward past the planets. This stream of charged particles, mostly protons and electrons, doesn't travel unimpeded. It eventually encounters neutral atoms like those of hydrogen gas that drift through the interstellar void within our solar system. When a fast-moving solar wind ion collides with one of these stationary neutral atoms, something fascinating can happen. An electron can literally jump from the neutral atom to the charged ion in a process called charge exchange. This seemingly simple atomic handshake has a dramatic consequence. The electron, now in a new home, often drops into a lower energy state, releasing its excess energy not as visible light but as a soft X-ray photon. This process is happening countless times every second throughout the heliosphere, the vast bubble of space dominated by the sun's influence. The collective effect is a pervasive, diffuse glow of soft X-rays that looks, to our telescopes, almost identical to the signal we might expect from the warm, hot intergalactic medium in the distant cosmic web. For years, astronomers were baffled by bright, patchy regions of soft X-ray emission that seemed to have no obvious source. It wasn't until they connected the dots to this charge exchange mechanism that they realized they weren't looking at the universe's hidden structure, but at the intricate weather patterns of our own solar system. Disentangling this local fog from the cosmological signal is a nightmarish challenge, as the intensity of this solar wind X-ray weather changes with the sun's activity cycle, creating a dynamic and shifting foreground that must be meticulously modeled and subtracted. Beyond the solar system, our local galactic environment adds another layer of complication. Our Sun resides within what astronomers call the local bubble, a vast cavity of low-density, million-degree gas stretching for hundreds of light-years in every direction. The leading theory suggests this cavity was carved out by a series of supernova explosions that occurred millions of years ago, their powerful shock waves sweeping up surrounding cooler gas and dust and leaving behind this hot, thin plasma. This searingly hot gas itself emits X-rays through thermal radiation, creating a soft, diffuse background that emanates from all around us. When we look out into the universe, we are always looking through this brilliant local fog bank. Determining how much of the soft X-ray glow in any given direction comes from this local bubble versus the distant cosmic web requires incredibly precise measurements and complex modeling of the bubble's shape and density, which we are still refining. The contamination doesn't stop there. Our galaxy is filled with countless stellar sources that contribute their own X-ray murmurs to the foreground. Vast populations of faint, unresolved white dwarfs, active stars with superheated coronas, and the remnants of dead stars all add their faint light to the mix. Even the solar system itself contributes. X-rays can be produced when comets, with their vast clouds of neutral gas, interact with the solar wind, creating temporary, moving points of contamination. All of these local effects coalesce into a brilliant and complicated foreground veil that lies between us and the pristine extragalactic signal. Peering through this veil to see the true cosmic X-ray background is arguably as difficult as the original challenge of resolving it into point sources. It requires a multifaceted approach, using observations at different wavelengths to map the structure of our local interstellar medium, monitoring the solar wind to understand charge exchange variations, and constantly improving our statistical models to separate the local from the cosmic. This ongoing battle against galactic contamination is a silent, painstaking war fought in data processing centers and supercomputer simulations, a crucial front in the larger campaign to finally understand the universe's first and most enduring light. To unravel the next layer of this mystery, we must journey back to one of the most pivotal and transformative epochs in all of cosmic history, the era of reionization. For hundreds of millions of years after the Big Bang, the universe was a profoundly dark and simple place. It was filled with a thick, neutral fog of hydrogen gas through which light could not freely travel. Then something extraordinary happened. The first stars and galaxies ignited, and their fierce, radiant energy began to tear apart those neutral hydrogen atoms, stripping away their electrons and flooding the cosmos with light in a process that astrophysicists call cosmic reionization. This was the universe's grand coming-of-age story, the moment it emerged from its dark ages and became transparent and ionized the way we see it today. For decades, understanding this epoch has been a holy grail of cosmology, and incredibly, the faint, ancient light of the cosmic X-ray background may hold the key to deciphering it. The central question of reionization has always been one of energy. What provided the immense number of high-energy photons required to strip electrons from hydrogen atoms across the entire vast universe? For a long time, the prime suspects were the first generations of massive, brilliant stars and the powerful ultraviolet radiation they blasted out. But there's a problem with this picture. While these stars were undoubtedly powerful, their UV light is easily absorbed. It doesn't travel very far before it bumps into another hydrogen atom and gets stopped in its tracks. This means you would need an impossibly perfect, efficient distribution of these first stars to ionize the entire cosmos without leaving behind any cold, neutral pockets. The math has never quite added up, leading scientists to search for another, more penetrating source of energy that could have helped complete this universal transformation. This is where X-rays enter the story. Unlike ultraviolet light, X-ray photons are the ultimate cosmic infiltrators. They carry so much energy that they can punch through vast clouds of neutral gas, traveling incredible distances before finally being absorbed. If the first stars and black holes in the universe were producing significant amounts of X-rays, they would have been the perfect agents for a process we call preheating. Imagine trying to defrost a vast, icy field. Ultraviolet light from stars would be like using a hairdryer, effective right where you point it, but slow to melt the entire area. X-rays, however, would be like switching on a giant space heater. They would have gently warmed the vast reservoirs of neutral hydrogen spread throughout the early universe, making it easier for the subsequent UV light to finish the job of ionization. This X-ray preheating could have been the critical catalyst that made the epoch of reionization not just possible, but efficient and complete. This theory transforms the cosmic X-ray background from a mere static glow into a unique historical record. Its specific spectral shape and intensity are a direct reflection of the total number and type of these first X-ray sources. By meticulously analyzing the background, cosmologists can run the clock backwards. They can use it to estimate how many of these early engines existed, how powerful they were, and crucially, when they first switched on. Did supermassive black holes form early enough to contribute their intense X-rays to the process? Or was the dominant source a vast population of the first X-ray binary systems, the remnants of those earliest short-lived massive stars? The answers to these questions are encoded in the light we receive today. However, extracting this information is a monumental challenge, akin to trying to hear a single, faint voice in a recording of a massive, crowded stadium. The X-ray light from the reionization era has been traveling for over 12 billion years to reach us. The expansion of the universe has stretched its wavelengths, shifting it from the high-energy X-ray band into the lower-energy extreme ultraviolet part of the spectrum. This means the specific contribution from the earliest sources is now blended into the overall background in a way that is incredibly difficult to isolate with our current telescopes. We are not looking for a distinct signal, but for a subtle distortion, a slight spectral skew that hints at the presence of these ancient pioneers. The quest to find this fingerprint is already shaping the next generation of space observatories. Missions like the European Space Agency's new Athena concept, or NAS, a proposed Lynx telescope, are being designed with the explicit goal of achieving the spectral resolution needed to perform this cosmic archaeology. They won't see individual first galaxies, but they will be able to detect the chemical signatures that their collective X-ray output imprinted on the intergalactic medium. It's a forensic approach to cosmology, where the crime scene is the entire universe, and the clue is a faint, all-pervasive glow that has been carrying its secret for billions of years. Unlocking it would finally reveal the complete story of how our universe turned on the lights, and the role that the most energetic photons played in sculpting the transparent cosmos we call home. But our investigation doesn't end with the relatively tame energies of X-rays. To uncover the next layer of this mystery, we must venture into a realm of almost unimaginable violence, a domain where particles are accelerated to energies that dwarf anything our most powerful machines on Earth can produce. This brings us to the fascinating and enigmatic connection between the cosmic X-ray background and its even more ferocious cousin, the TV gamma ray background. While X-rays are powerful, gamma rays represent the absolute peak of the electromagnetic spectrum, carrying millions of times more energy per photon. A TeV, or tera-electronvolt, is a unit of energy so colossal that a single photon at this level carries roughly the same kinetic energy as a flying mosquito, all packed into a subatomic particle. The existence of a diffuse background of these monstrous photons adds another profound layer to our cosmic mystery, and its surprising correlation with the X-ray background hints at a fundamental connection that could point to the universe's most extreme particle accelerators. For a long time, these two backgrounds were studied by separate communities of astronomers using entirely different telescopes and techniques. X-ray astronomers looked at the sky with instruments like Chandra, while gamma-ray scientists used vast ground-based arrays that detect the faint flashes of Cherenkov radiation produced when these high-energy photons smash into the Earth's atmosphere. It was only when researchers started to compare the all-sky maps from these different regimes that they noticed something startling. The large-scale distribution of this incredibly energetic TV glow seemed to loosely mirror the smooth, isotropic nature of the cosmic X-ray background. This was more than a little surprising. You wouldn't necessarily expect the processes that create million-degree temperatures and X-rays to be directly linked to the mechanisms that can accelerate protons and electrons to 99.9999% of the speed of light to produce TV gamma rays. This correlation suggests that we might not be looking at two separate choirs, but a single cosmic orchestra where different instruments are playing different but harmonized parts of the same terrifying symphony. So what kind of cosmic engine could possibly produce both of these signals simultaneously? The prime suspect is a class of objects known as hadronic accelerators. The key to understanding this lies in the two different ways that high-energy radiation can be produced. The X-ray background is largely dominated by what we call leptonic processes, involving light particles like electrons. When a fast-moving electron is deflected by a magnetic field, it releases X-rays through a process called synchrotron radiation. This is efficient, but it has an energy limit. To reach the unbelievable energies required for TV gamma rays, you need to involve the heavy artillery, protons. Hadronic processes occur when protons, the nuclei of hydrogen atoms, are accelerated to near light speed and then slam into other protons or photons. These spectacular collisions create a shower of secondary particles, including neutral pions, which almost immediately decay into pairs of gamma-ray photons. An object that can accelerate both electrons and protons would therefore be a factory for both X-rays and gamma rays, a perfect candidate for a source that contributes to both backgrounds. This theory points a direct finger at some of the most violent and powerful objects in the universe. Supernova remnants, the expanding shells of debris from exploded stars, are prime candidates. Their shock waves are perfect natural particle accelerators, capable of boosting both electrons and protons to relativistic speeds. As the electrons spiral in the remnants' magnetic fields, they generate X-rays via synchrotron radiation. Meanwhile, the accelerated protons collide with ambient gas in the interstellar medium, triggering the hadronic cascade that produces the high-energy gamma rays. Galaxy clusters, with their immense gravitational wells and turbulent magnetic fields, could also act as colossal reservoirs for these accelerated particles, their combined output contributing to both backgrounds. But perhaps the most compelling suspects are once again active galactic nuclei. The relativistic jets launched by supermassive black holes are arguably the most powerful particle accelerators in the universe. Within these jets, all the necessary physics could be happening on a gargantuan scale, with internal shocks accelerating particles and producing a broadband spectrum of radiation that stretches from radio waves all the way up to TV gamma rays. The implications of this correlation are staggering. If a significant portion of both backgrounds originates from the same population of sources, it provides a powerful new tool for understanding the most energetic processes in the cosmos. By studying the ratio of X-rays to gamma rays, astronomers can potentially peer into the heart of these accelerators and determine their fundamental properties. For instance, a high ratio of gamma rays to X-rays would suggest an environment that is exceptionally efficient at accelerating protons, a hadronic-dominated universe. This would be a monumental discovery, as it would finally allow us to quantify the elusive cosmic rays, the charged particles that permeate space but are impossible to trace back to their sources because magnetic fields bend their path. The gamma rays they produce, however, travel in straight lines, acting as unambiguous arrows pointing back to their origin. The combined study of these two backgrounds could therefore solve two mysteries at once, revealing not only the sources of the high-energy light, but also finally identifying the powerful engines responsible for the cosmic rays that have baffled scientists for over a century. This synergy between different windows on the universe is transforming astrophysics, turning a multi-messenger approach into our most powerful tool for deciphering the cosmos's most violent secrets. Yet for all our grand theories about cosmic webs and dark matter, one of the most persistent and humbling challenges in unraveling the mystery of the cosmic X-ray background comes not from the depths of space, but from the intricate engineering of the telescopes themselves. This is the often overlooked but critically important problem of instrumental calibration. Imagine two world-class musicians trying to play the same piece of music in perfect unison, but one of their instruments is tuned just a fraction of a note sharp while the other is slightly flat. The resulting discord would make it impossible to appreciate the true beauty of the composition. This is precisely the situation astronomers face when trying to combine data from different X-ray observatories. Each telescope, a marvel of human ingenuity, has its own unique design, its own set of detectors, and its own subtle, built-in biases. These differences mean that when two telescopes look at the exact same patch of sky, they can, and often do, return subtly different measurements of the brightness and the spectral shape of the CXB. The core of the problem lies in the fiendish difficulty of calibrating an instrument that is designed to detect photons with energies thousands of times greater than visible light. You can't simply point an X-ray telescope at a known bright star and adjust the settings as an optical astronomer might. The universe doesn't provide convenient, standard cosmic candles that shine with a perfectly predictable and unwavering intensity in the X-ray band. Instead, scientists must rely on a painstaking process of cross-calibration, using a handful of the brightest and most stable X-ray sources as benchmarks to carefully align the measurements from one telescope with those from another. But even these so-called standard candles have their own complexities and can exhibit faint variability, introducing tiny, compounding errors into the process. Furthermore, the mirrors and detectors in an X-ray telescope degrade over time, bombarded by the very radiation they are meant to observe, causing their response to slowly but surely drift. This means that a measurement taken by the Chandra telescope in 2003 might not be directly comparable to one taken by the same instrument in 2013, let alone to one from XMM Newton or a newer mission like New Star. These calibration uncertainties have real and profound consequences for our understanding of the CXB. The most significant discrepancy revolves around its absolute intensity, essentially, just how bright this pervasive glow really is. For decades, different missions have reported values that disagree by as much as 20 to 30%. That's a colossal margin of error in a field where scientists are often arguing over fluctuations of 1% or less. This isn't just a minor academic disagreement, it strikes at the heart of the entire endeavor. If we can't agree on the total amount of light, how can we possibly hope to account for it? A higher measured intensity would require a larger population of hidden sources to explain the glow, while a lower intensity would suggest our current inventory of black holes and galaxies might be closer to complete. This calibration rift means that two different research teams looking at data from two different telescopes can construct two entirely different and equally valid models of the high-energy universe. The conflict extends beyond simple brightness into the precise shape of the background spectrum, the detailed breakdown of how its intensity changes across different energy levels. This spectral fingerprint is our primary clue for identifying the types of sources that contribute to the glow. Does the spectrum show a sharp cut-off at high energies, suggesting a dominance of certain types of black holes? Or does it have a specific bump or dip that points to the presence of hot gas or dark matter decay? The answers depend on exquisitely precise measurements. Yet, because each telescope's detectors have slightly different energy resolutions and response functions, the reconstructed spectrum of the CXB can look different depending on which instrument you trust. A feature that looks like a tantalizing signature of new physics in one dataset can vanish entirely when viewed through the lens of another telescope, reduced to a mere calibration artifact. Resolving this impasse is not a task for astronomers alone. It requires a collaboration with physicists and engineers in a dedicated, ongoing campaign of precision measurement. The effort involves using particle accelerators on Earth to fire X-rays of known energy at test versions of the flight detectors, meticulously mapping their response. It involves developing complex computer algorithms that can model and correct for the effects of instrument degradation over time. And it involves organizing large, coordinated multi-observatory campaigns where several telescopes simultaneously observe the same celestial target to directly cross-check their measurements in real time. This meticulous, unglamorous work is the essential foundation upon which all of the grander cosmic theories are built. It is a reminder that before we can hope to understand the secrets of the universe, we must first master the intricate quirks of our own extraordinary machines, ensuring that when we finally listen to the cosmic symphony, we hear it not through distorted instruments, but in its true and magnificent clarity. And yet, despite this compelling narrative of a universe woven together by hot gas, the ledger of cosmic matter still refuses to balance perfectly. We now return to the missing baryon problem, but with a specific and critical question. Does the cosmic X-ray background finally provide the proof we need to close this embarrassing accounting error for good? The theories are elegant. The WIM saturating the cosmic filaments should contain the missing half of all ordinary matter. But in science, elegance must bow to evidence, and the current evidence presents a frustrating and complex picture where the numbers, despite decades of meticulous work, still stubbornly refuse to add up to 100%. The challenge begins with the sheer difficulty of taking a cosmic census. We cannot simply put the entire universe on a scale. Instead, astronomers must use indirect methods to weigh the unseen, and each method comes with its own set of uncertainties and assumptions. The primary technique for finding the WIM has been the study of absorption lines, those tiny fingerprints imprinted on the light of distant quasars. By analyzing these dips in the spectrum, scientists can estimate the density and total mass of the hot gas in the specific filament the light passed through. When they extrapolate these point measurements across the entire cosmic web, the numbers start to look very promising. Some studies suggest that this hot intergalactic medium could indeed account for a large portion, potentially even all, of the missing baryons. It's a compelling result that points toward a solution. However, other measurement techniques tell a slightly different story. Another way to hunt for the WIM is to look not for its absorption, but for its extremely faint emission, the collective diffuse glow that might be part of the CXB. By carefully subtracting the light from every known point source in a deep X-ray image, the remaining truly unresolved flux could be the signature of this web. But when astronomers attempt this painstaking accounting, the numbers they get for the mass of this emitting gas are often lower. They suggest that while the WIM is undoubtedly there and contains a vast amount of material, it might only account for perhaps half to two-thirds of the total missing matter, not the full amount. This creates a troubling discrepancy between what we infer from absorption studies and what we measure from emission. Part of this confusion stems from the intricate and clumpy nature of the cosmic web itself. The WIM is not a smooth, uniform soup. It is a dynamic and structured ecosystem. It exists in a variety of phases and densities. Some filaments are denser and hotter, shining more brightly in X-rays and leaving stronger absorption signatures. Others are more tenuous and diffuse, their signal so weak it falls below the detection threshold of our current telescopes. Furthermore, this gas isn't static. It is constantly flowing, cooling, and heating. Some of it might be cooling down and falling into galaxies, transitioning from the hot WIM phase into colder, atomic gas that is easier to see. Other parts might be getting reheated by shock waves from cosmic structure formation or by outbursts from active black holes. This constant churning means the amount of mass in the hot phase is not a fixed number, it's a snapshot of an ongoing cosmic cycle. Our measurements might be capturing this complex system at a particular moment, but missing other components that are transitioning between states. This leads to a fascinating and more holistic possibility, that the missing baryons aren't in a single hiding place, but are distributed across several different reservoirs, each contributing a piece to the puzzle. The cosmic X-ray background, therefore, might not be the signature of one solution, but a combined chorus from many. The warm, hot intergalactic medium in the filaments is likely the largest repository, but it may not act alone. A significant amount of mass could also be hiding in the extended, hot halos that surround individual galaxies like our own Milky Way. These circumgalactic media are enormous atmospheres of multi-million-degree gas, and while they contribute to the overall X-ray background, their mass is incredibly difficult to pin down because they blend seamlessly with the larger-scale WIM. Furthermore, a portion of the missing matter might be in forms that are even more difficult to detect than the WIM. Could there be a population of cold, dark gas clouds, devoid of stars and difficult to see at any wavelength, drifting in the voids? Or what about the mass locked in extremely low surface brightness galaxies that have evaded our optical surveys? The CXB, as a cumulative record, would include the light from the hot gas within these structures as well. The grand total of the missing baryons might not be found in one colossal treasure chest, but in 1,000 smaller caches scattered throughout the cosmos. The unresolved glow we see is the sum of all these contributors: the brilliant unresolved AGN, the muffled whisper of the WIM, the collective murmur from galactic halos, and the faintest sighs from every other hidden pocket of ordinary matter. Until we can perfectly disentangle each voice in this cosmic choir, the final accounting will remain just beyond our grasp, a testament to the universe's endless capacity to conceal its secrets in plain sight. For 60 years, the cosmic X-ray background has been a siren's call to astronomers, a beautiful and frustrating puzzle just beyond the reach of our technology. But what if I told you the tools to finally solve it are already on the drawing board, and in some cases being built right now? This isn't science fiction. It's the thrilling reality of the next decade in space science. We stand on the precipice of a new golden age of discovery, powered by a generation of X-ray observatories so advanced they will make our current telescopes look like fuzzy binoculars compared to the Hubble Space Telescope. These missions, with names like Athena, Lynx, and XRISM, are not merely incremental improvements. They are quantum leaps designed with one overarching goal: to finally, decisively unravel the secrets of the cosmic X-ray glow. Leading this charge is the European Space Agency's Athena, the advanced telescope for high-energy astrophysics. Scheduled for launch in the mid-2030s, Athena is a behemoth conceived not just to observe but to perform cosmic tomography. Its key instrument is the X-ray Integral Field Unit, or XIFU, a technological marvel that will provide spectroscopic resolution over 100 times better than any current X-ray telescope. To understand what that means, imagine today's instruments can identify the general color of a distant galaxy. Athena's XIFU will be able to distinguish the exact shade of every single star within it all at once. This incredible capability will allow it to do what was previously impossible: map the velocity and turbulence of the hot gas in galaxy clusters and the cosmic web with breathtaking precision. It will hunt for the faint emission lines of the warm, hot intergalactic medium, not just in a few lucky sight lines toward bright quasars, but across vast stretches of sky, effectively creating a three-dimensional map of the universe's missing baryons. Furthermore, its wide-field imager will conduct deep surveys that will resolve virtually all of the remaining unresolved background into individual point sources, finally identifying the legions of hidden, Compton-thick active galactic nuclei that have eluded us for so long. Athena promises to transform the WIM from a theoretical concept into a charted territory and complete the census of supermassive black holes across cosmic time. While Athena will provide unparalleled spectral vision, NASA's proposed Lynx X-ray Observatory is designed to offer an equally revolutionary leap in sharpness. If approved, Lynx would have the highest angular resolution ever achieved in X-ray astronomy, allowing it to see with stunning clarity. Its mission is to peer into the dawn of the first black holes. With resolution so sharp it could distinguish a single star at the distance of the Andromeda Galaxy in X-ray light, Lynx will be able to look back to the universe's infancy and directly observe the accretion disks around the first supermassive black holes as they began their frenzied feeding. It will see not just the brilliant quasars but the fainter, more numerous precursors, understanding how they grew so massive so quickly. This will directly address the first black holes problem by providing a direct observational census of these ancient monsters. Furthermore, Lynx's incredible sensitivity will probe the faintest end of the X-ray source population, hunting for the stellar mass black holes and neutron stars in the halos of galaxies whose collective murmur might account for the missing galactic X-ray emission. It will see so deeply and so clearly that it will effectively eliminate the confusion limit, resolving the vast majority of the point sources that currently blur together into the unresolved background, and leaving behind only the truly diffuse emission from the hot gas of the cosmic web for us to study in pristine detail. But we don't have to wait until the 2030s for progress. The recently launched XRISM mission, a collaboration between JAXA, NASA, and ESA, is already serving as a vital pathfinder, testing the next-generation technology that will power these future giants. XRISM flagship instrument, Resolve, is a precursor to Athena's XIFU, a high-resolution spectrometer cooled to within a fraction of a degree of absolute zero. While its field of view is smaller, it is demonstrating the transformative power of microcalorimeter technology. Right now, XRISM is collecting spectra of galaxy clusters and active galactic nuclei with a fineness of detail never before seen, allowing scientists to measure the composition, velocity, and turbulence of hot plasma with unprecedented accuracy. It is, in essence, perfecting the techniques and proving the science that Athena will later execute on a colossal scale. The data from XRISM is already being used to refine the models and observational strategies for its larger successors, ensuring that when Athena and Lynx finally launch, we will know exactly where to point them and how to interpret their revolutionary data from day one. The breakthroughs we can expect from this coming fleet are not mere incremental additions to our knowledge. They promise to be paradigm-shifting. Within the next 2 decades, we fully expect to have a complete and accurate map of the warm, hot intergalactic medium, finally closing the book on the missing baryon problem once and for all. We will have a definitive census of active galactic nuclei across all of cosmic history, understanding the life cycle of supermassive black holes from their mysterious origins to their quiet old age. We will know if the faint, anomalous X-ray line at 3.5 kiloelectronvolts is truly the signature of dark matter decay or simply a complex atomic process, potentially solving one of physics' greatest mysteries. These telescopes will not just resolve the cosmic X-ray background. They will deconstruct it, attribute each part of its symphony to a specific player in the cosmic orchestra, and in doing so, they will write a new and definitive chapter in our understanding of how the high-energy universe evolved, from the first flickers of light after the Big Bang to the grand, structured web of galaxies. See today, the long night of mystery is ending, and a new dawn of understanding is just over the horizon. But beyond the technical specifications of future telescopes and the precise accounting of baryons lies a final, deeper layer to this mystery, one that transcends data and probes the very nature of our quest for understanding. For 6 decades, the cosmic X-ray background has been more than an astronomical puzzle. It has been a profound philosophical mirror, reflecting both the audacity of our curiosity and the humbling vastness of our ignorance. Its pervasive, unexplained glow challenges not just our models of stars and gas, but our fundamental place in the cosmos and the limits of our perception. To truly contemplate this mystery is to ask what it means when 98% of the high-energy light in the universe comes from sources we cannot name, and what it says about us that we are driven to try. At its heart, the CXB is a stark reminder of the universe's overwhelming neutrality to human concerns. It is a phenomenon that existed for billions of years before the first life forms appeared on Earth, a constant, energetic sigh that has permeated the void completely unnoticed until one particular species on a tiny rock around an average star developed the technology and the will to look up and ask why. There is a certain cosmic irony in the fact that this most universal of signals, this background radiation that is quite literally everywhere, was discovered entirely by accident while searching for something else. It whispers that the universe is not designed to reveal its secrets easily. They are hidden in plain sight, waiting for the right combination of chance, ingenuity, and persistence to be brought into focus. This challenges the anthropocentric notion that we are the center of anything. We are instead privileged observers in a grand, dynamic theater where the main action is still largely occurring behind a curtain we are only just learning how to pull back. The enduring resistance of the CXB to a single, simple explanation also forces a humility in our scientific approach. For every elegant theory, be it the warm-hot intergalactic medium or legions of hidden black holes, there exists a complicating piece of data, a calibration uncertainty, or an unresolved fraction that prevents a clean victory. This is not a sign of failure, but a testament to the complexity of the reality we are trying to comprehend. It teaches us that our models, no matter how sophisticated, are always approximations. They are maps of a territory that is infinitely more detailed and surprising than we can imagine. The CXB keeps us intellectually honest, preventing cosmology from becoming a closed book and instead ensuring it remains a living, breathing, and contentious field of discovery. It is the anomaly that protects science from dogma, the unanswered question that guarantees there will always be a next chapter to write. Furthermore, the very nature of the background, its apparent uniformity, presents a profound puzzle about perspective and scale. From our vantage point, the glow is isotropic, a perfect smoothness that suggests a homogeneous universe. But we know this is almost certainly an illusion, a statistical averaging of countless clumped sources across such immense distances that their individual identities blur into a single haze. This is a powerful metaphor for the limits of our perception. What appears from our limited viewpoint as a fundamental, smooth property of the cosmos may, in reality, be a trick of the light, a consequence of our inability to see the intricate, lumpy details from so far away. It asks us to consider what other truths about the universe we are misunderstanding because we lack the resolution to see the intricate patterns hidden within what we perceive as uniform. Ultimately, the philosophical weight of the cosmic X-ray background rests on what its final resolution will represent. If the missing flux is definitively traced to the hot gas of the cosmic web, it will be a monumental triumph for the standard model of cosmology, confirming our deepest theories about how structure forms and where the universe hid its atoms. It would be a story of completion, of finding the last pieces of a puzzle we largely understood. However, if a significant portion of the background is ultimately explained by something more exotic, the decay of dark matter, the collective murmur of primordial black holes, or a previously unknown physical process, it would represent something far more thrilling, a paradigm shift. It would mean that the universe has been quietly signaling a deeper layer of reality all along, one that we were previously blind to. The CXB would then be remembered not as a puzzle to be solved within our existing framework, but as the first clue that led us to an entirely new framework, a new understanding of the fundamental constituents and forces that shape existence. In this way, the faint X-ray glow that bathes the cosmos is more than just ancient light. It is a question written across the sky. It asks how much we can truly know and how comfortable we are with the unknown. Its eventual resolution will not just close a chapter in astronomy. It will define the nature of the next one, revealing whether our current vision of the cosmos is largely correct or merely a prelude to a far stranger and more wonderful reality waiting to be discovered. The mystery endures not as a failure of science, but as its greatest inspiration, a permanent invitation to look deeper, think harder, and remain forever in awe of the universe's endless capacity to surprise us. So after this incredible journey through the depths of space and time, what have we truly learned? We began with a simple, uniform glow and discovered it contains not one, but 25 of the most profound mysteries in modern science. We've grappled with the baffling uniformity of this radiation, a perfect smoothness that contradicts the lumpy universe we see. We've hunted for the missing matter that should be there but has eluded every search, and we've considered the possibility that the answer lies in a hidden web of searing hot gas strung between the galaxies. We've looked to the awesome power of supermassive black holes, only to find they can't account for everything, forcing us to search for a secret army of obscured monsters shrouded in cosmic dust. We've examined the colossal energy of galaxy clusters and found them to be mere bit players, and we've been surprised by the significant hum coming from countless quiet stars. We've entertained the breathtaking possibility that this glow could be the final signal of dark matter itself, slowly dissolving into light. We've used the background as a time machine to peer back at the first, impossibly massive black holes, and we've been puzzled by why our own galactic neighborhood seems oddly dark in comparison. We've seen how this ancient light might hold the key to understanding how the universe woke up from its dark ages and became transparent. We've followed the trail into the realm of unimaginable energies, connecting the X-ray glow to its ferocious gamma-ray cousin. And we've acknowledged the painstaking challenge of simply calibrating our instruments to hear this cosmic whisper clearly. We've seen how the answer might not be one thing, but a complex symphony of sources, from the hot gas in filaments to the faintest stellar remnants, and we've recognized the constant contamination from our own solar system's weather. Through it all, we've run headlong into the resolution paradox, where better telescopes only reveal how much we have yet to find, and we've relied on massive supercomputer simulations that still can't quite reproduce the universe we see. What ties these 25 mysteries together is a single, powerful truth. The cosmic X-ray background is so much more than a faint glow. It is the ultimate cosmic puzzle, a single phenomenon that connects the largest scales of the cosmic web to the smallest particles of dark matter and the present-day universe to its very first moments. It is a reminder that for every question we answer, the universe reveals two more, each more fascinating than the last. This 60-year detective story is far from over. The next chapter is being written right now in laboratories and engineering clean rooms, with missions like Athena and Lynx preparing to launch us into a new era of discovery. They promise to transform this faint, uniform haze into a detailed map of creation, to find the missing matter, and to finally listen to the individual voices in the cosmic choir. The greatest takeaway is this sense of wondrous anticipation. We stand on the edge of a new frontier, knowing that the answers are out there, hidden in the light, waiting for the next generation of explorers to finally bring them into focus. This story isn't ending, it's just getting started, and the next breakthrough could be just one observation.